Hi everyone, my name is Vadid and I am a civil engineer. In this session I am just going to talk about the drainage design that is useful for the civil engineers and whoever designed the drainage network, particularly in the UK, because we have to go through several steps. So let's get started. So in the UK we have actually the five stages. So one is the pre-application, and then we have the outline stage. In the pre-application we just need the basics, for example flood risk assessment reports, and then we have the outline stage where we just provide the strategic, for example you have the 2D layout, but then we have the full planning. In the full planning we have to provide the comprehensive guide from full design of our drainage network, like what will be the runoff, how we will handle the water throughout our site, and how we are going to discharge our network. And then we have the reserved matters. This also includes the detailed engineering and then network modeling, and obviously the layout finalizing. And the last, we also have the fifth stage, that is discharge. Like this is for the CIRIA 104 adoption plans. So most important is for the full planning and the reserve matters, because this includes our full drainage design and all of this information that are required. So these are the basically the planning stages in the UK. So it's very important that you understand what stage the client asks you to work on, and then you will work through those stages, and you will have the idea what you are going to design. And then these are the checklist that I have here. You can say, so in this one we have the flood. So I have made some of these like descriptions, and then we will have the application stages. For example, pre-application we need the drainage strategy only, like the 2D plan. You can just say that the manholes or the water will be here, but not the fully detailed design. But for the outline or the full planning stage, you need the detailed design, and you need the full calculations as well. And similarly for the reserve matters, you need all of these one, like grounded with infiltration, to see the soil is clay, like the soil is clay or sandy, or what type of soil is, the infiltration rates. Like you should know that if you can provide the soakaways or the any attenuation that can help the water to be attenuated on the site. This is the discharge agreements is usually the section 104 or section 106. So these are basically the checklist that I have made for better understanding that at what stage what we need. So and then we have this one. This is basically CIRIA SuDS guidelines, and in this one you will have the first choice is, like for example if I will say that what is our first choice, like first choice is the infiltration, or you can say that infiltration you will see if the site is available, that it's not very much clay, that you can create the soakaways or you can create a pond or something, and then this is the infiltration. Then the second choice will be the watercourse, like if you have any ditch passing through, if you have a already water channel, that you can discharge your water to that watercourse. And then the third choice will be the last one, and that's the discharge to the surface water sewer network, that they have the separate surface water network. And then the last one will be the combined sewer network. So as an engineer, once you are on the site or you have the basic plans and you go through the ground investigation reports, then you will find out that what is the first priority can be. If the soil is like clay, then obviously it's very hard to go for the soakaways, but if you have a good soil, uh, then you can go for the infiltration. So this is the first priority, then you go to the second, and then this is the third preference, and this is the combined sewer network, like if you don't have any other option available. So these are the SuDS manual guidance, so you should keep in mind before designing this. And in the coming videos I will show how we can design different designs for a site in InfoDrainage. And then we have this one. These are also from the SuDS that we have to make sure that we are managing the quantity of our site, like we are not putting a lot of runoff into the public drainage network or public sewer network, like the government agencies pipe network, and then we may ensure that the quality is good, like we are not detaining water for so long in our ponds that that the quality of the water goes down. So we have to make sure the quality, and then that it's also safe for the environment, safe for the people, because designing the pond you make sure that the slopes are not very steep, like someone fell down, or if you have some slopes that could be dangerous, you provide the fences around this one. So this is the basic, like you have to make sure that this is safe for the environment, for the species, and then the biodiversity, obviously, that it doesn't have a lot of concrete. You can, as long as you can provide a bioretention basins, that could be more handful. And yeah, we will also design that in InfoDrainage. So these are the basic terms that I want you guys to know, because these are mostly used and asked when we are writing the reports, or whenever we are designing something. We should have all of these things in our mind to process, to think about anything. And then this is an important thing. You can see the hydraulic neutrality. What it means is that if we have the pre-development conditions should be less than or equal to post-development. So it means if we have some site, for example, we have a site, let's say this is a site, and it has the rainfall, and this is a green field, like this isn't developed. So let's suppose it has some runoff of, like, say 6 liters per second, and we are now planning to design a housing development or some commercial state on this one, and this is the same site, but this is like post-developed. So it's post-developed site. So we have to make sure the runoff on this side is not exceeding that was previously calculated, that was 6 liters per second. For example, now this side shouldn't be discharging 7 liters per side to the water channel that was like, say, somewhere here. So we have to make sure that we give some attenuation, where like we have to control by a little small ponds, or by we should have some kind of break here that is not discharging so long into the water. This can be otherwise this isn't going to be approved, because this is not a engineering practice where you are not limiting your discharge. So we have to provide the flow controls to limit the discharge from the green fields, like to the water channels, and then we also make sure that we can provide attenuations, for example the ponds, fields, or bioretention, permeable pavements. But it's our responsibility that the runoff that we have calculated for the pre-development is not exceeding the post-development. And also we will see how we can calculate that in the InfoDrainage as well. For example, for our site, to calculate our pre-development green field runners rates, and then we will also make sure that our post-development runoff rates are not exceeding to the pre-development rates. Otherwise, obviously, your design is just useless because you are flooding, you are risking the flood into the public sewer network. So this is very important to understand, that these are the stages in order to design something for the drainage design, for the swale, for the pond design. So all of these steps should be kept in mind as we'll see how we can create those in the coming videos. And then we have the Q bar. The Q bar is basically the mean flood value. So in some situations, for example, there is for example, a soil is very sandy and you have got the pre-development conditions are like 1.5 liter per second, and it's very hard to achieve those once you will have a site, once you have a post-development. Obviously, once we will have the development, we are going to have more roads. We will have more roads, more footpaths. So these things will obviously impervious, and then it will also discharge more runoff. So in order to, and the preconditions were 1.5, and we are not like, we cannot reach at that minimum value, minimum discharge. So in that case, the Q bar value comes in, that this is basically the mean annual flood. So this is, we calculate for the 2.33 year return. So we will first calculate our Q bar value. We calculate the Q bar value for the 2.33 return period, and then we use that as our pre-development conditions, and then we use this one as a pre-development, and then post-development will be compared to this one to make sure that we are not discharging the excess water into the any of the water course. So this is can be very useful. So this is a small site, for example, sandy ground, and the ground feed rates can be lower than 2 liter per second. So this one can be risky because it can cause the clogging, and again, you know, the quality. So this will make the quality of the water poor. So that's why we will go for the Q bar values, because we have to make sure the quantity, and then quality, then amenity, and then amenity and environment, was it? Yeah, biodiversity. So yeah, so this will help us to design the practical design of sound engineering design for our drainage network. So this will be the blockage free. This will be the blockage free and maintainable. So we have to think all of these things in our mind, so in order to design our network, drainage design network. And then we have some of that inputs that we use in the InfoDrainage. So these are the SAR, that is standard average annual rainfall. That is also, this changes from region to region. So some regions have different SAR values and someone has different, but in the InfoDrainage you just pick up a region. You make sure that the region you have selected is proper. So once you select the proper region, it comes up with the SAR value, that is from FSR, that is FSR is the flood studies report, and then we have FEH, that is more advanced stage, that is latest, and that is called flood estimation handbook. So you can just download the data from the FEH website and then put into the InfoDrainage, and this will comes with more advanced rainfall information, rainfall data. So this is for the SAR values are calculated automatically in the InfoDrainage, and then we give the soil types, and soil types obviously come from the ground investigations. So if you have the ground investigation report, it will tell you the soil types, but basically and mostly commonly in the UK is clay soils. So clay soils are impermeable soils. They are not very good in permeability. So it comes with the values. So we will give the we will give the input the soil type value into the InfoDrainage to calculate that how much the soil is impermeable, that the water will infiltrate or not, or how we are going to control our discharge from our site, and also make note that clay requires more attenuation tanks because the soil is not very much permeable, that you cannot create the soakaways that the water will go into the ground and it will just stay on the ground. So this way we will have to make sure that we have giving on the side proper tanks, proper ponds, so that the water is not there isn't any risk of flooding. So these are the values that we also input. This comes from the automatic that once we select the region, and this one is from the ground investigation, and we can use the values like 0.3, 0.5, whatever the values we will have. We will see in the once we will be practically designing the InfoDrainage model into the into our software InfoDrainage. So these are basically the inputs. So and then we have the features that most commonly we can use. We can use the detention ponds. So these are the like ponds if the soil is good and if we have a space on our side. So first of all, our preference is to provide a drainage of a detention pond. So this will be high capacity, and it is also biodiverse, and it is keeps the quality of the water also very nicely. And then we have other option is the grassed swales. So swale is basically, for example, you have site here and then you want your water to flow. Instead of using the pipes or underground sewer network, you can use greenfield areas, and then the water flows from one area to one region to B to any region. This is particularly within the same site, same discharge area. So in this way, some of the water will infiltrate and some of the water will go, instead of going to the grey network, the pipe network, it goes to the green network, that is the swales. And then water goes from one to other one, and then this way some of the water will infiltrate and some will be controlled, and then we can utilize our green areas more perfectly. And then we have the bioretention. So these are the rain gardens. For example, you can see that you have a footpath, and then the footpath, some portion of the footpath is you can put the green belt here, put the green trees here. So like as much as water you can store on the side that cannot go on that doesn't cause the flooding. Let's say that you have this big site. So previously it used to have the pond here, and this was all, you can say, the grey structure, the buildings, the roads, the footpaths, and all of these impermeable surfaces water goes into the pond. So what can it do? It will increase the risk of flooding. But then it comes new things. You can see BMP, best management practice, or LID, low impact development. You can say SuDS, sustainable drainage solutions, drainage systems, and what Australia called it WSUC. So Australian called it water sensitive urban drainage. So all of these terminologies are mostly interchangeably, and they have the same mean that we have to lower the risk of flooding in a site. So previously the designers use this approach, like you have all of this runoff and then just put a detention pond here, and this will all be all store the water here. But then the new, as soon as like research happened, and then we came to see the different approach. For example, this is a big site, and then you can provide the pond here, like one pond here, and then for example you can put a rain garden, like small garden for like children's playground, and this can be the rain garden. This can store some of the water. You can have the permeable pavements. You have some commercial market and you can just provide the permeable pavements that the water go into the ground. And then, for example, you can have some trees, big trees here. This can also soak the water into the ground, and in this way the runoff we were on the side that was going into this pond is comparatively very low compared to the previous stage, like previous concept. And this is also known as sponge cities, sponge city. So this is also known as sponge city approach of designing something, because in this way you just distributed the water. For example, instead of this is the road, this is a road, and this is another road. In the center we can put some of the swale, that we can put the grass and then trees, and that the water, once the rainfall happen, the water will go into this swale, and some of the water will infiltrate, and from there it can go to this playground. From, if it's risk of flooding, then it can go to this permeable pavement, and then if it's risk of flooding, then it can go into the pond. So this way we have done is distribute the runoff. It's not like we just store it in a pond and then wait it to infiltrate, but to distribute in the network. So this is basically the best approach in order to design the cities, in order to design a residential development or mixed use urban drainage designs. But also you have to make sure that you are not using a lot of space. You have to make the value engineering, that you are not like putting everything green. You have to make sure that you are providing a sound engineering, value engineering, and you are also also making sure that the risk of flooding is very low. So this is basically, we will also see like which approach we should apply in our practical designs. And these are all features available in InfoDrainage, and we can provide the hydro-break control networks, flow control, and then bioretention, whichever is one. And if you guys have something else, we can also see how we can design any concept we can design. And then this is the return periods. Return periods are like 1 in 30 years storm. So for example, the rainfall, that storm that comes, that has a chance of 1 in 30 years. So for example, in the previous 30 years, the type of the biggest storm ever came, that was called 1 in a 30-year storm. So this is we use for the capacity our drainage network, that our drainage shouldn't be should not flood once we run it on the 1 in 30-year analysis. 1 in 30 years is like 30-year period. You have a 30-year period, and the storm, you will have all the data of that 30-period network, that region, and then 1 in 30, like that has the probability of one time in 30 years. So we use that data to calculate that our capacity is well enough that it's not flooding. And then we have 1 in 100-year storm, that in the previous past 100 years, the biggest storm that ever happened. We have that data, and we will run the analysis, run the simulation to see if our model, how it reacts to that storm, and if it's like totally flooded, or we have the capacity and we have utilized 100% of our on site. And then we have the climate change values, that's 40%, but this is to see what happened. Is it like it was like catastrophic, or what happened to that one? So this is, we will also run the simulation to analyze the data, how we can improve our design, how we can liaise with our local flood authorities, any discussions with them, any solutions, any ideas. So we can also run these simulations as well. So also we have to check 10% urban creep. So urban creep is basically to put 10% extra, that in future, like some people will change their gardens into the pavements. Like if you will see in the villages, there used to be more gardens, but then once the cars arrives, and then they will start changing gardens into the garage so that they can park their cars. So we just 10% is like if someone changed or something happened that we have to convert our greenfield area that is already in the development into the urban, into the impermeable services. So this way we can also put the 10% urban creep to see how our model reacts to that one. So this is all the simulations back and forth, and we will go through how we can do this, but these are the major steps that every engineer should know. And then we are just the final notes, I would say, that make sure that you have 10% urban creep as you always design for the worst case scenario as an engineer. So this is your urban creep exceedance, that you should make sure that the system is not pressure very much, that it can handle safely and effectively the site and the infiltration, so that we first of all we will design as per the infiltration, that if we can use our water to infiltrate into the ground, yes, then we can design, no, then we will find the other solutions. And then if the site testing reveals clay, assume zero infiltration, and then we will obviously, if the clay site is the impermeable soil, then we will design some other geocellular tanks or some other features that we can use according to our needs, according to our site. So these are the main things that I have discussed today. So if you guys have any questions, please ask in the comments, and make sure you guys remember these things, because in the coming videos I am going to go through the practical design in the InfoDrainage. So it should be better that you understand the compliance, the regulatory information. So it's I mostly focus on the UK design, but all over the world it's more or less the same. For example, pre-development conditions should be less than the post-development conditions, and then this is the sponge cities, and then swales, pond. So this is overall used everywhere, but a little bit different terminologies. But I will be focusing on compliance and regulatories within the UK, and we will be see how we can design these ones in the InfoDrainage. And even if you have any ideas like how we can design better, we can see how we can try that as well, if we can have better solutions. So I hope you guys like this presentation or lecture or whatever, or session. If you guys have any questions, just ask in the comment section. I will be happy to help. See you in the next video. Peace out.